Okay, so last time, let's start this example problem. Work through this example problem. So we've got a weighted piston cylinder, contains 0.3 kilograms of steam. By the way, anytime you see steam in this text or in my notes, steam simply refers to water. Okay? So that's really all they're telling you. They're saying steam refers to water. So, piston cylinder contains 0.3 kilograms of steam at 1 megapascal, 400 degrees C. Determine the boundary work if the final state is 1 megapascal and 250 degrees C. All right, well, let's set this up. I think we can do that. So, common procedure for a thermo problem would be, what are you looking for and what do you know? Well, we're looking for, they want us to find the boundary work. Now again, I don't require you to write the entire problem statement. If that helps you, by all means do. I don't require that. You really should, though, when you're writing out a solution, what is it you're looking for? Because you'll get, when these problems are going to start getting really long, you're going to get really lost at some point and say, what the heck are we trying to do? It's always nice to have home base. You can go back and say, what am I looking for? I'm looking for the boundary work. Okay. Then we start saying, all right, well, what are the tools I have to find the boundary work? Well, first and foremost, you need to know, what do you know? What is the information that's given? They've given me that I've got a piston cylinder. The easy things are the numbers. They said, well, the mass is 0.3 kilograms. I've got a pressure of 1 megapascal and a temperature of 400 degrees C. Okay? And then they say, all right, well, then you've got a final state. So you have two states here. So I'm going to put a 1 on these. These are my initial states. And then they've given me a final state down here. P2 is also 1 megapascal. And T2 is 250 degrees C. Now, they've also told me that it's water. How do I know that? Because they call it steam. Anytime they say steam, they're referring to water. That's really the only major assumption you can make. Be careful making any assumptions about the phase. Most likely they're telling you it's going to be in the vapor phase. That doesn't mean it's saturated, superheated. We're not sure. We have enough information. We can go figure that out, though. So that's going to be one of the challenges, figuring out what kind of vapor are we talking about. But when they say steam, they're referring to water. And just because the problem statement says you have water doesn't mean that it's in the liquid phase. You need to look at the properties it's given to figure that out. There's one more thing that's given. Always look at your adjectives. What are your adjectives telling you? This is a weighted piston cylinder. So they're telling you the pressure is constant, which we can kind of see here, but we really don't know what happens from here to there unless they told us. You can assume that pressure is constant. Now that's going to be important because, again, I'm looking for boundary work, and we say, all right, what are the tools? So the next step in the procedure is after we know what we're looking for, we know what we know, okay, what are some tools I have to find this? What are some good ways to find the boundary work? That's kind of the standard procedures. What are you looking for? What do you know? What are some good tools to find it? Well, the best tool, there's two tools that come to mind. One is the first law, okay? One is the first law, which maybe we write that down first, but I would suggest to you there's most likely heat transfer occurring, which there's actually on this diagram here. There's actually heat transfer occurring. I don't know the heat transfer. That's going to be an unknown in the first law. So you could write the first law. You're just going to have more unknowns than you can solve for. However, we do know the boundary work expression. By definition of boundary work, that is going to be the integral of pressure with respect to volume. Now, I keep calling this W sub B, comma, out, meaning I'm going to compute boundary work in the out direction. If I'm computing boundary work in the out direction, then I'm integrating from V1 to V2. And we can expand on that after we get done with this problem. But I'm integrating from V1 to V2. That is boundary work out. if you want to find the boundary work in, flip the sign of the integral, put v1 up here, v2 down there, and you can find the boundary work in. Here we're going to find the boundary work out. Okay, so if I try to find the boundary work out, and we say, all right, well, what do I know about so I've got some unknowns here, right? Or maybe I've got some unknowns. I know the pressure at these different states. I also know how pressure, right? How is pressure as a function of volume? That's the first question we've got to ask. Well, how does pressure vary as a function of volume? Well, it's constant. Right? So it's constant. So this is actually a pretty simple integral. The boundary work out, I can pull this pressure out of the integral. So pressure, then I'm going to integrate from V1 to V2 dV. Right? Pressure's constant, comes out of the integral. And then I'm just integrating dV. Well, in your calculus class, when you integrate dx, what do you get? You just get x. So in this simple problem, this is P V2 minus V1. Okay. I know pressure. So the next step, right, so we said, all right, what are we looking for? What do we know? What's a good tool to get there? Then the next step is say, all right, well, after I've simplified this as far as I think I can go, do I have all of my knowns, right? Or do I have as many unknowns as I have equations? I only have one equation here. Boundary work is equal to this expression. So that means I can only have one unknown to solve this one equation. So that means I need to know my pressure, which I do. I need to know my volumes, which I don't have, because I need this to be my only unknown. This is what I'm looking for. So for this to work, this needs to be my only unknown. I need to know these. So how do I find these? Well, recall specific volume is volume per unit mass. And the reason that helps is because based on my pressure and temperatures and the fact that it's water, I can use my property tables to find specific volume and then use the mass to find the total volume. So I can find specific volume at state 1, specific volume at state 2 that gives me the total volume. Okay. There's another way, you'll probably see this a lot of times. If your mass is constant, which this one is, if your mass is constant, that can come out of the integral. Right? So I could say this is the integral of from, let's say, mass times pressure with respect to little volume. This expression is just fine. Right? This is this expression. I've just pulled the mass out of the specific volume, out of the total volume. And if I'm doing this, then I'm integrating with respect to specific volume. And so I just need to put little v's on there. Now the mass is constant and the pressure is constant, so those can both come out of the integral. I'm integrating from little v1 to little v2 with respect to little v, or specific volume. And so this is equal to mp delta little v. Either way works, right? This is just fine. Find total volumes using this logic, or use it in the calculus also. Either one's fine. I'm probably going to use this one. Okay. Now, I know the mass, I know the pressure, I need to go find these specific volumes. So now I'm at the point of properties. Okay, so now I'm looking for properties. Well, how do I find properties? Well, we go back to the multi-step process we talked about in lectures 5 and 6, and we say, well, this is a scenario in both cases. This is a scenario where I know pressure and temperature. Right? So given pressure of 1 megapascal and a temperature of 400 degrees C, I need to go find the specific volume at state 1. And then knowing pressure at state 2, also 1 megapascal, and the temperature at state 2 is 250 degrees C. If you'll set this up, if this were a test problem, this is a little too simple for a test problem, but if you would set this up as a test problem, you're going to get most of the points right here. You show me you know how to get to a solution. you've shown me you know what is unknown, you know how you're going to get those unknowns. Now it's literally just looking up properties and doing some algebra. So I would suggest you've done 80% of the work at this point. I try to set up my grading scale to where you get as close to a B as I can get you at this point. Now, if it's an online test, it's a little different because we've got the timed questions and then you're working a solution. But setting the solution up should still work the same way. I'm pulling my property tables out here. Oh, I think I've got those in the notes. So let's just. Right. So what I would do in class, if you guys were in front of me in class, is at this point I would say, all right, well, go pull out your books and read these off so I don't have to look these up. Now I happen to have these here. V1 is, I have got written down here 30661 meters cubed per kilogram. Now if you're getting something different, write it down in the comments and we can adjust that. Right? If you look at these up and by the way, you need to learn how to look these up. Right? This is important. This is a small step in a bigger problem. So we got to get really good at these. I mentioned earlier, you're going to go through this process 100 times of finding table properties. I was not kidding. And that's just getting started. V2, if you look this up, I'm getting 0.23275. That's meters cubed per kilogram. Again, if you're getting something different, write it in the comments or check the comments. Maybe somebody's already commented they're getting something different. That's perfectly fine. I will mess these up sometimes. Okay. All right. So now I've got everything, right? This is my only unknown. Now it's just time to solve for this. Right, now I have this written down. I'm trying to keep this short. Run this through your calculator, right? Boundary work out is equal to 0.3 kilograms. That's my mass. Times my pressure, 1 megapascal, times my change in volume. V2 is 0.23275. I'm going to factor my units out, just write them one time because it's the same units for both of these. 0.30661. Both of these are meters cubed per kilogram. I'll move that down so you can see it a little better. Okay. Again, you run these through your calculator. I happen to have the answer over here. I'm getting minus 20. Now, if you run these numbers through, you're going to get minus 0.02216, right? And then we look at the units and say, well, that's megapascals meters cubed. I've got kilograms divided by kilograms. So it's megapascals meters cubed. Now if we look at our units there, the first question is, what units would you like? Well, it's a work term. So any unit of energies would be good. Joules would be awesome. Well, let's look at these. A pascal times a meters cubed is going to be, a pascal is it's pressure, so it's force per area. That's Newton per meter squared times meters cubed. So this becomes a Newton meter. So a pascal is a Newton meter, which is a joule. Make sense? A pascal meters cubed is always going to be a joule. So a megapascal meters cubed is going to be a megajoule. And I might suggest let's convert this to kilojoules. It's 22.16 kilojoules. Notice the negative sign. This is smaller than this. Right? So I'm going this way. So this is a negative integral. I would get a negative area. What is that telling me? That's for the next video. We'll talk about that in the next one.